Hey physics students, welcome back to another episode of Rapid Review for Honors Physics. Today we're going to talk about ramps. Okay, so this is all about problems on an incline. You may remember that when we studied rolling balls, we tipped our coordinate system and we said that was totally fine. We're going to do that here too. In fact, that's the first of the several steps for solving problems on forces on ramps. Let's get right into it. I'm going to start with step one here, which is to tilt the axis. I'm setting up a coordinate system that matches the running surface of the ramp, the top surface of the ramp. Remember, we're allowed to do this. It's arbitrary however we orient it. You could try to do it up and down, and you will find everything works out perfectly in solving problems. The only thing is the math gets a little more messy and it's unnecessary. So it's kind of a nice trick to know that you can tilt the axis and the math gets a little simpler. Let's take a look at what happens once we set up that coordinate system. We can show the forces acting on the object, and here I'm looking at a typical problem where there's an object sitting on a ramp, and you can see that right away two of the forces, the normal force and the friction force, are already nicely aligned with the coordinate system. The only thing we have to resolve into components later will be F sub g. I point out now that the forces are shown symbolically, F sub n, F sub g, right? I do that because I don't know what the numbers are yet. And also, it just helps to be able to label everything early in your force diagram so that you can refer to it later. If you do the force diagram carefully, it's a lot easier to write the algebraic equations you're going to need to use to solve the problem. So we're back to this. We have things labeled now symbolically, and we're going to resolve the vectors into the new coordinate system. The only one I have to deal with here is F sub g. You will notice that I show its components, F sub g in the x direction, F sub g in the y direction. Remember, that's my coordinate system. And I show my original force as a dotted line here. You might also, if you're going to write over your existing diagram, you might want to kind of scribble it out or something to be clear so that you don't end up with forces and their resolved versions of the same force all in one diagram. It gets messy, it gets confusing, it's easy to make a mistake. So either cross out your old force when you break it into components, or better, if you're willing to do it, is draw two different force diagrams. First you draw the force diagram the way I did, and then you draw what we would call the modified force diagram, in which all of the forces are shown in their components parallel to the coordinate system. Okay, so be careful with that. And okay, so now I have resolved these vectors. Notice in this equation here on the slide that F sub g in the x direction is Fg sine theta and y cosine theta. It might at first confuse you, like, why is that? I thought x components were a cosine thing, like when we did projectiles. Don't fall for that mistake. Do convince yourself that these equations are correct. The reason you might be confused, if you are at all, is that this theta here on the ramp and this theta here are the same theta, and you could show geometrically that that's true. You could do a little geometric proof. I will skip that. But notice how the green theta is measured from horizontal, where the red theta is measured from vertical, and that's why the sine and cosine are what they are. Take a look at that closely, make sure you understand that, and you'll avoid making a common mistake. Finally, you'll solve equations as needed. Let's look at an example. Here, we're given a theta of 30 degrees and a mass of 10 kilograms sitting on the ramp, where the coefficient of static friction is given as 0.2. Does the object slide? Classic question. Here's a solution to that. It's pretty straightforward now that you've solved problems already with friction. In the y direction, the normal force is the same as F sub g in the y, which we've already calculated, and we get a number for that. In the x direction, force of G in the x direction has to get calculated, and we do that work. I'll skip all the intermediate steps here. You can freeze the slide if you want to see the details. Finally, I calculate F of friction max, right? This is max static friction. And as you recall, it's necessary when we solve problems to first figure out whether static friction applies or kinetic friction applies. In fact, in this question, the whole question was, is it sliding? You know, which kind of friction applies? Let's take a look. It seems in this calculation, the maximum possible static friction was 17 newtons, and that's trying to oppose 49 newtons that was applied by F sub G in the x direction. So yes, the object slides. Yes, check. We got that one done. Okay, so let's see. That's very similar to problems that you'll see elsewhere. Everything's a variation on that. The key are to follow the steps, to tilt your coordinate system, and to break things into their components. After that, the equations begin to almost write themselves. Okay, so watch out for that. Conceptually, theta does a lot of things in these problems, and it's worth looking at that. I call it thinking about theta. If we look at the slide, you'll see my force diagram, and I have several different questions about theta. I'm going to step over to the demonstration table here and show you what theta might do at different angles, right? So as theta increases, F sub G in the x increases. Take a look at the force diagram. I'll switch to that over here in the video, and you'll see that F sub G in the x is bigger if theta increases. Also, FG in the y is less. Why? Let's look at the ramp again. Oh, there's less normal force. The more I come up, the less normal force there is, and therefore the less F sub G in the y. Take a look again at the diagram. You'll see that F sub G in the y, as it gets smaller, means the normal force gets less. If I'm sliding in kinetic friction, that means that, oh, less normal force, mu k times F sub n. Oh, yeah, if I have less normal force, I'm going to have less sliding friction as well. So what happens is two things conspire to make the block move faster. If you look again at the ramp, you'll see that if I get a bigger F sub G pulling down and I get less friction pulling back, both of those things contribute to this thing going faster and faster as the ramp is steeper. And this all makes sense with your everyday experience. So study that slide if you were at all unsure about the concepts of what the theta means, because I think if you understand the answers to all those questions, you'll do quite well. Let's take a look at the last bit that I have to show you. It's a very interesting special case, and it's called critical angle. So the critical angle means, what if I have an object and I tilt the ramp just enough so the object slides? I'm going to do that with my cutting board and my phone, and I'm just going to tip it towards you, and I'll catch it, I hope. Oh, there it is. So there's an angle at which the phone began to slide. If I can measure that angle, it's interesting to note that I can figure out what the coefficient of static friction is just from that one little experiment. Okay? We do a lab on that, but if you want to see the derivation, you can freeze the video and look at how I derive it. Here, I will just jump to the conclusion, which is pretty cool. What it says is, if you look at now the slide here, the coefficient of static friction is the tangent of theta that I just measured. Or, to say it the other way, the critical angle theta is the inverse tangent of mu static. So if I want to get mu static, all I have to do is tilt the thing until I get the thing to start sliding. I take the tangent of that, and I get my answer for mu static. What's amazing about that is it's independent of m. So if my iPhone were heavier or lighter, it wouldn't matter. As long as those two surfaces were the same, I'd be measuring the coefficient of static friction with that experiment. So I think that's enough on that. You can try this at home with things like at the breakfast table. You can throw your maple syrup on your cutting board and impress your friends and family, and perhaps you'll do a lab like that too. But I don't need to do that lab here for you. I'm sure you can try it at home. And with that, I will leave you and wrap up this topic of ramps. See you next time.